last time we talked about determining our order of reactions for the kinetics of a single reactant reaction. All right. Now, if we have multiple reactants, then what we're going to need to do is we must determine the order for each of our reactants in the reaction, and we must include all of our reactants and the orders in our rate law. Okay? So for example, say we have NO2 plus CO goes to NO and CO2. We would write our rate expression as the rate equals, our differential rate law as the rate equals our rate constant times NO2 to the M order times our concentration of CO to the N order. Now, if we had more reactants, we would just continue to add those with a different letter for each of their orders. And we would have to determine their order for each of those different species. All right. Now, say that we've got a table of data here, okay, for this given reaction. Notice that we have 3 different trials. We could have as many as we wanted, okay, but we're also going to have the concentrations of each of these different components in the reaction, okay? And notice that each of the trials, in some of them, they have the same concentration, okay, and in some of them they have different. We also have our rates, okay? Now the reason that some of them are going to have the same concentrations is because when we do our ratio, following those steps that we had in our last video, we're going to want to hold one of them constant while we change the other one, okay? So for example, right, first we're going to identify the species that we want, okay? So in this case, let's do our NO2 first. So I'm going to say pick one. All right, and I'm going to pick the NO2. So I've got my concentration of NO2. The very next step, all right, will be to find 2 rows in which the concentration of that species changes, but the other ones are held constant. All right, so here I want to find 2 rows where my concentration of NO2 changes, okay? So 1 and 2 change, and notice that CO does not change. So that means that I can use 1 and 2, all right? Now, notice that 2 and 3 also change my concentration of NO2. However, my concentration of CO also changes. So I cannot use 2 and 3 for the calculation, okay? We can only change one of our columns at a time, okay? So I'm going to pick rows 1 and 2, okay? Then I'm going to set up my ratio and solve for the order. All right, now I want to put the bigger on top, right? So we're going to put 2 over 1, row 2 over row 1, okay? And for that, I first put my concentrations, 0.200 molar over 0.100 molar, right? And then I put my rates. Again, I'm going to put row 2 over row 1, just like we did last time. 4.42 times 10 to the negative 6th over 2.21 times 10 to the negative 6th. Notice that if I do this division, I get 2. And then on the right-hand side, I get 2. All right. And I'm going to use the letter that corresponds with whatever I had in the first part. So that means that my order has to be first order for the NO2. All right, so I now know that my M is equal to 1. All right, then following the same procedure, all right, I just did the NO2. Now what I'm going to do is I'm going to pick the other species, and I'm just going to work my way through my rate law. So the next one is CO. So I'm going to take my concentration of CO, all right, and I'm going to look for a row where the CO concentration changes, okay, but none of the others change. All right, so if I have the case where my CO changes and the others stay the same, notice that 1 and 2, I didn't change my concentration of CO. All right, well, let's try 2 and 3. Well, my concentration of CO changes, but so does my concentration of NO2. So I can't use that one either. But notice that 1 and 3 are different, okay, in my concentration of CO, but they have the same concentration of NO2. So my CO changes for 1 and 3, but my NO2 does not. Okay, so that satisfies it. So we can use rows 1 and 3. All right. Now, let's set up our ratio and solve. We're going to pick our bigger of the concentrations and put that on top. So we're going to put row 3 over row 1. All right. Our concentrations get listed first, so we have 0.200 molar over 0.100 molar. And then we put our rates. So I have 8.84, again from row 3, 8.84 times 10 to the negative 6. And I'm going to put that over 2.21 times 10 to the negative 6. All right, dividing through, I get 2 times on the left. Remember that we're going to raise the left-hand side to whatever power we had. And then on the right-hand side, we have 4. Okay, now what power does n have to be in order for this ratio to be true? Well, n is going to have to equal 2. All right, because 2 squared equals 4. So I now know that my overall multiple reactant rate law is going to be that the rate is equal to our rate constant times NO2 to the first power times our concentration of CO to the second power. All right, so let's do some more practice with this. Okay, let's say that we have this reaction where we have 2NO plus 2H2 goes to N2 plus 2H2O. Well, following these steps, all right, let's first write down what our overall rate law would be in terms of N and M and L and Q and whatever other letters you may need, right? So we will have rate is equal to our rate constant times our concentration of NO times our concentration of H2. Oh, I'm sorry, times our concentration of NO to the M times our concentration of H2 to the N. Okay? Rate constant times our concentration of NO to the M times our concentration of H2 to the N. All right? So working our way through this, first we're going to pick one of our species. And again, if it appears on the left-hand side, right, or if we're working from that particular side of our reaction, then we know that all of these components are going to go as our concentrations here. Okay, so if I had, 2NO and 2H2, right, then I'm going to have NO and H2 as my concentrations, and then we have to figure out what the orders are from the table. Okay, so we need to first, let's pick our species. Well, our first species working through the table is going to be NO. All right. Then for our second step, right, we need to find rows where our NO changes, but the others stay the same. All right. Well, notice that 1 and 2, they change, and the H2 stays the same. So does that work? Yes. Again, in rows 1 and 2, our concentration of NO changed, but our concentration of the other species stayed the same. All right, so then we're going to build our ratio, and I'll do that below here. Okay, so our ratio, which one's bigger? row 2, so we're going to put that on top, row 2 over row 1. All right, and then I'm going to have my concentration, which is 0.500 molar over 0.250 molar. And that's going to be equal to our rates, right? And again, we're going to go with row 2 on top. So we have 2.46 times 10 to the negative third, and row 1 on the bottom, which was a 1.23 times 10 to the negative third. All right, looking on the left, if we do the division, we have 2x, and on the right-hand side, we also have 2x. The left-hand side gets raised to whatever power we have here, so we have m. So that means that m, in order for this relationship to be true, m must be equal to 1. All right, so we have the concentration of NO to the first. Okay. Now, working our way through, we've done NO's order. Now we need to do H2. All right. So we want to find rows where H2 changes, but our NO does not. All right, well, we could do, looks like 1 and 3. That would change our H2, but notice that our concentrations of NO also change. Because the concentrations of NO also change, we cannot use rows 1 and 3. So let's take a look at rows 2 and 3. Yes, we have a different concentration of our H2, and notice that we do not have a different concentration for our NO. That means that we can use rows 2 and 3. All right, so looking at rows 2 and 3, we're going to take the bigger row, not necessarily the bigger number of the row, but the bigger concentration, the row with the bigger concentration. We're going to put that on top. So row 3 has a bigger concentration than row 2. So we're going to put row 3 over row 2. All right, which means we're going to have 0.500, starting with our concentrations, over the 0.250 molar. All right, and then over here we have 2.46 times 10 to the negative third, and we have 2.46 times 10 to the negative third. All right, and if we take our left-hand side, we have 2x raised to the n, again using our power from up there. All right, and then notice here we have 1x. It didn't change. That means that our n has to be equal to 0. Remember that for a zeroth order reaction, okay, our rate won't change even if we change our concentration. Okay, so that means that our concentration of H2 is raised to the 0 power. All right, so that would be how you would get your differential rate law and the orders using experimental data. All right. As always, if you guys have questions, feel free to reach out. Please also let me know how you feel about the pace, right? If it's too fast, let me know. If it's too slow and you guys are bored, let me know. All right. I can try to give you guys some more examples, or I can try to pick up the pace if you'd like. All right. I want to make sure that we are delivering good education for you guys. So you got to let me know how I'm doing, so that way I can adjust things to help you all out. I assume that you guys are liking the examples. That seems to be pretty consistent with what you guys have said so far in the emails that I've gotten. All right, but keep letting me know and keep giving me feedback, because I want to make sure y'all are doing okay. All right. Now, the next thing that I want to do is I figure we can do maybe one more example of the calculation for determination of orders. So let's do slide 14 next. All right. Now, sometimes in your table, you may actually have some changes, right? So that don't always make sense when you're plugging in your numbers. but as long as you follow the steps, you should be okay. So let's say we have NO2 plus CO goes to NO plus CO2. All right. What is our rate law going to be in terms of order M and N? Well, we know that we're going to have our rate constant. We're going to have our concentration of each species raised to a different power, right? So we have our concentration of NO2, that's our first species, raised to the M. Then we're going to have our concentration of our next species, which was CO, raised to the N, okay? So that's going to be our initial kind of setup for our rate law, okay? Now, if I gave you data that was trial 1, 2, 3, and again, all of this data is on those slides that I've posted on Canvas, okay? So be sure if you want to print those out. You guys can pause them and write it down, that's fine too, but I think it's probably easier if you print out the slides and write on those. Then we have our concentration of NO2. We have our concentration of CO. And then we have our initial rate. Okay. Here we have 0.100 molar, 0.200 molar, 0.100 molar. In the next column, we have 0.100 molar. We have 0.100 molar, 0.200 molar. All right. And then for our rates, we have 2.21 times 10 to the negative 6. We have 4.42 times 10 to the negative 6. And we have, that's a 6. And then we have 8.84 times 10 to the negative 6. Okay. Now, if we were going to try to find our orders for this, right, and this is that same example that we did before, but I wanted to show you kind of how we go through the process, even if we don't have nice numbers that always work out, okay? If you just happen to take one that changes, okay, what you're actually doing is you're saying, okay, let's say I'm going to take trial 2 and put it over trial 1, okay, like row 2 over row 1. That's going to give us our rate, right? We can take the entire reaction and put it over the entire other reaction. So we would say that we have our rate, right? I'm just going to write this here. We have our rate is equal to K NO2 to the M, CO to the N, okay? So this is where that kind of ratio comes from. I'm going to take my rate from trial 2, which was 4.42 times 10 to the negative 6 over, and I'm going to say that that's equal to, right, K times my concentration of NO2 from that row, which was 0.2 molar, right, and that's raised to the M, and then I had 0.1 molar raised to the N, okay, again going with my different species in the row, right? And I'm going to put all of that over my rate expression, or sorry, my rate law for trial 1, which was 2.21 times 10 to the negative 6. And then you have K and 0.1 molar to the M and 0.1 molar to the N. Okay? This will always give you the right orders, all right? Because you can cancel your K's, you can cancel your M's, right? Depending on which ones you have. And then notice that this is how you get to on the left. And then notice how I have my concentrations raised to that power, right? That's what gives me the 2 to the M, okay, which allowed me to get M is equal to 1. Okay, and I just wanted to walk you through this at least once so that way you understood where those ratios came from. Okay, but you can always use the steps that I've already given you. Okay, now moving on, the next thing that I'd like to talk with you all about So we talked about our differential rate laws. Okay, now I want to talk about integrated rate laws. So let's move to slide 15. Okay, and we'll talk about integrated rate laws. Now, those of you who are taking calculus right now or who have taken it in high school, okay, the way that you get your integrated rate laws is you actually integrate your differential rate laws. All right, I'm just going to show you what they are. You just need to know, if you haven't had calculus, you just need to know the equations that I'm going to give you. Okay, so let's say that we have the integrated rate law for 0th order. Right? If you have 0th order, right, we had a differential rate law where the rate was equal to K times my concentration of species raised to the 0 power. All right? Now, what that means is that we will be able to have an integrated rate law of the concentration of A equal to negative KT plus my concentration of A at the beginning. So this is the A at time t. This is the A at time equal to 0. My concentration of the species at the final time, my concentration of A at the initial time. Okay? Now, I will expect you to have this memorized and this memorized. Okay? You need to have your differential rate law and your integrated rate law memorized for each of the first 3 orders. Okay? So 0, first, and second order. All right? Now, since this, as you can see, right, this will be, and notice that that's a negative, this is basically like saying y is equal to mx plus b, right? Where b is my y-intercept, so I know that, and my slope is negative, right? M is equal to negative k, right? So that means that my graph for this will start at my concentration of A initial, that's my y-intercept, and it will be a negative line, a negative straight line, okay, where the slope, right, M is equal to negative K. All right? So this would be my concentration on this axis, and this would be my time on that axis. So this would be for the 0th order. All right? Now, covered 0th order. Let's introduce first order. So on slide 16, first order is going to be a little bit different. All right, for your first order, we start with our differential rate law, which was that the rate was equal to our rate constant times our concentration of A to the first power, right? That's our first order rate expression, all right? Now, using calculus, we're going to integrate this, and what we get for our integrated rate law is the natural log, the ln of A, is equal to negative KT plus the natural log of our initial concentration. All right? Again, I expect you to have that memorized. Now, using this is also in that form y equals mx plus b. So if we were to plot this, right, our y-intercept would be at the ln, or the natural log of our initial concentration. That's where we start. And then our slope is also negative k. as we go across time. Okay, so our concentration decreases over time, all right, where the ln is our y-intercept, okay? So that covers our first order and our zero order. Now, again, using calculus on slide 17, don't worry, I'm just expecting you to have the final result memorized. I'm not going to show you all the steps. All right, on slide 17, we look at our second order. Integrated rate law. Okay, so for this, we have R is equal to K times our concentration of A to the second power, and that gives you, so that's our differential rate law, that's going to give us our integrated rate law of 1 over our concentration in A at time t is equal to positive KT plus 1 over our concentration of A at the beginning. Again, A is just the species that we're looking at. Okay, so that would be your second order integrated rate law. Now, again, it's in the form y equals mx plus b. So if we plot this, all right, we are going to start at 1 over our initial concentration on the left-hand side. That's going to be our y-intercept. And notice that this time our slope is positive. Okay. All right. Where, of course, as we go across time, 1 over our concentration will increase. Okay, so this axis is 1 over our concentration of A. So if we wanted our concentration of A at a specific time, we would have to calculate it, and then we would take the reciprocal of that to get our final concentration. Okay? Now, let's see. I think that this is probably a good place to stop. Well, maybe. Yeah, I think this is probably a good place to stop. That way I can draw the next figure. All right, so I will see you guys in the next video to finish our orders and begin our half-life discussion.